So this is our introduction to simple harmonic motion. Um, let's go ahead and get started. Let's start by defining a few important terms here. First, let's make a note of the different types of motion that we may encounter, and each of these is sort of a subset of the previous. So the first thing we can talk about is just simple periodic motion. This is motion that repeats with a well-defined cycle. It's a motion that repeats in time, and the time for that repeat is consistent. We call that the period. So a person pacing back and forth in a room could be an example of periodic motion. Now, oscillatory motion is a little bit different. It looks like periodic motion. Say that person pacing back and forth happens, it could repeat very, very regularly. It's not oscillatory. Oscillatory motion occurs because there is some force that is drawing an object back to an equilibrium position. Now remember from the first semester definition of equilibrium, the net force when an object is in equilibrium, the net force is equal to zero. In oscillatory motion, when an object is displaced from that equilibrium, a force pushes it back towards that equilibrium. So the most common example, the one we're certainly going to be talking about the most, is going to be the case of a mass on a spring. A spring has an equilibrium length, and when it is in that position, there's no net force. On the other hand, if you compress the spring, the spring pushes back towards the equilibrium position. If you extend the spring, it pulls back towards the equilibrium position. That's going to produce oscillatory motion. And you can see why that's saying something different than just periodic motion. When a person is pacing back and forth in the room, there's no force that's actually drawing them back towards the center. On the other hand, if you have, say, something like a snowboarder on a half pipe going back and forth from side to side of the pipe, that is, in a sense, a very real example of oscillatory motion. There is a force drawing them back toward the center of the pipe. It's gravity. Now, the last two are going to be distinctions that are going to be made more clear as we go on with our mathematical description. What we're going to see is that there is a class of oscillatory motion that is very well described by sinusoidal functions, the sine or the cosine, and we call that subset harmonic motion. And because this motion can be described by sums of these sines or cosines, multiple sines or cosines added together, we make a distinction between that sort of general case of harmonic motion that may be described by multiple sinusoidal functions added together, and simple harmonic motion, which is harmonic motion described by a single sinusoidal function. Let's go ahead and talk about that case a little bit more. Well, let's go back and dig into our equilibrium positions a little bit more. You may have seen this first semester. Let's talk about this here. So recall that in equilibrium, the net force on an object is equal to 0. So if you take the case, we have a couple of cases that are shown in the graphic there. We have and in each of these we have a ball that is presented on some kind of surface, a concave surface, a bowl on the left-hand side, a convex surface, a hill on the in the center, and a neutral surface, a flat surface on the right. And these three images represent our three types of equilibria. In the left-hand image, if that ball is displaced a little bit from the center, gravitational force will draw it back towards the center. This is what's called a stable equilibrium. The displacement from equilibrium results in a force directed back towards the equilibrium position. So drop a marble into a bowl, or skater on the half pipe that I mentioned previously. Those are cases of stable equilibria. As long as you're at the bottom of that bowl, you're in equilibrium. Anywhere else, you're not, but the force is directed back towards that equilibrium position. That's distinctly different from the middle case, where we have the marble on the top of the hill. Here, while at the very top of the hill, the net force on the object may be 0. We have a normal force directed upward, gravity directed downward. If we displace a little bit from that equilibrium position, either to the left or to the right, there's an additional component of gravity directed toward or down the hill. So if you displace a marble a little bit from the top of the hill, it'll continue rolling down the hill on either side. We call that an unstable equilibrium. It's certainly possible to balance the ball at the top of the hill. There is that equilibrium position there. But if we displace even just a little bit, it'll roll away and it won't come back. The last case is our neutral equilibrium. And in our neutral equilibrium, I do have my pointer, thank you. In our neutral equilibrium, we're sitting here in an equilibrium position. And if we displace just a little bit to the left, we're still in an equilibrium position. A little bit to the right, we're still in an equilibrium position. There's no force that shows up or develops regardless of how we move this. Now, in order to get oscillatory motion, we're going to need to see this case. We're going to see this stable equilibrium, so we can have a force directed back towards that equilibrium position. So the easiest way to start talking about simple harmonic motion is to take a spring and a mass. Now, you should have seen at least a little bit of Hooke's law forces in the first term. If not, we'll just quickly remind you of what a Hooke's law force looks like. Any spring has the ability to compress or extend, and it requires an amount of force that is proportional to the distance that it is stretched. The proportionality constant is called the spring constant or the Hooke's constant and is represented by a K. So if we come down here to our Newton's second law equation, so there's our general form of the Newton's second law equation, the net force acting on the object on the left-hand side, mass times the acceleration, the change in the object's momentum, on the right-hand side. So in our image here, where we have a simple mass on a spring, there are no forces acting other than that elastic force, the Hooke's law force. That negative sign indicates that the force is always opposite the direction of the displacement. So if we displace the object to the right, x is positive, and therefore the force is negative. If we displace the object to the left, the displacement is negative, and then the force becomes positive. The greater the spring constant K is, the stiffer the spring is. The harder it is to compress or extend, the more force it exerts. All right, so there's our picture here. And to remind you, that spring constant is measured in newtons per meter. All right, so we take our Newton's second law equation, and one of the things we like to do with this is rearrange it to a zero sum. So you can see how we've performed a little bit of algebra here. We've moved everything over to the left-hand side. So we have the acceleration plus this ratio of the spring constant to the mass multiplied by position equals 0. And we call this, in general, not just for simple harmonic motion, but in general, we call this the equation of motion. Now, this particular equation of motion is really kind of interesting. It's a little bit different from a lot of the Newton's second law equations that we've talked about before. Remember that acceleration is a time derivative of position, the second time derivative of position. So if we go back and take a look at that equation of motion, equation 2, we can utilize this description of the acceleration to rewrite our equation of motion in terms of x and time. And this is really kind of a fun equation because we have x in both of these terms. But it's not x, it's x and how x changes in time. This is a differential equation, and if you've heard of differential equations, if you've taken differential equations, then you look at this and you say, oh, I know all about a differential equation like this. If you haven't, you may have heard scary things about differential equations. They're not. They're fantastically useful expressions that allow us to relate parameters like position to how those parameters change in time. Now, we're not going to dig into the ugliness of how you actually solve a differential equation here. That's beyond the scope of this course. However, we can show that the solution to this differential equation is fairly straightforward. So that solution in this case looks like equation 5 listed here. So this is a solution to the equation of motion, which is to say this is an equation that shows us how position changes as a function of time. And it tells us that in this case, when we have a problem that has this equation of motion, either equation written as equation 2 or as equation 4, that the solution will be a sinusoidal type function. Now remember that when we say a sinusoidal function, that does not mean just a sine function. It means a sine or a cosine. They look the same other than being shifted off from one another by 90 degrees. But this particular position function is sinusoidal in time. Now, without digging into what these terms mean, let's demonstrate that this is actually a solution. So even if we can't derive it ourselves, we can assure ourselves that this is valid. So we're going to take our position function x of t, and we're going to take two derivatives. The first derivative will get us to velocity, and the second derivative will get us to acceleration. So we take the first derivative of our position function. Velocity is the first derivative of position with respect to time. And so we're going to kind of write this out in the standard way. A is a constant, so the time derivative slips inside that. And we apply the chain rule. The derivative of cosine is negative sine. And then we apply that derivative to the argument of the cosine function. So argument of omega t, the derivative of omega t with respect to t is omega. The derivative of delta with respect to t is 0. Delta is a constant. And so we end up with minus a omega sine omega t plus delta. We can take a second derivative to get to the acceleration, or take the first derivative of the velocity function with respect to time, and again, apply that time derivative to the velocity. Minus a omega comes out front. Derivative of sine is cosine, and the derivative of the argument of the sine function is omega, which we'll throw in over here to get minus a omega squared. Okay, so we're going to put all these things together, or actually we're only going to put the acceleration and the position equations together. So we're going to take our equation 5, we're going to take our equation 7, and we're going to plug them into our Newton's second law equation, a plus k over mx. So we've thrown, here's our acceleration, here's our position, and we are going to end up with, I see I've simplified this a little bit faster than I had meant to. With a little manipulation, we can recognize that, oh, actually, I apologize. I lost track of where I was. We can see this, we have the same cosine omega t plus delta term in each of these added terms. So let's factor that out. Let's divide both sides by cosine omega t plus delta. Let's also divide both sides by a. When we do, we're going to be left with just that minus omega squared from the first term and plus k over m here. So these things are constants. All of these terms are constants. So this is a solution to Newton's second law as long as omega squared is equal to k over m, which is shown down here in equation 9. Okay, so let's do a little bit of exploration of this equation. So we're going to come back to our position function. I'm going to have you plot this up. Now, you may have a graphing calculator. Great. If you don't have a graphing calculator, or you don't have a graphing calculator handy, let's go to, open up a Google tab in your favorite browser, and we're going to use it to plot. If you've ever used Google to plot before, then you know what you're doing here. If you haven't, this is pretty straightforward. So go to a Google search bar, and type the following line, shown here and shown down in the screenshot down below. So plot y is equal to 1 times cosine 2 times x plus 0. Now, the astute person should, of course, will recognize that 1 times will not change the value of anything, but we're going to change that here in a few minutes. All right, so you should get a graph. It'll show you a graph that looks something like this. And if you scroll your cursor across that plot, you'll see the values, x and y values change here. So you can inspect this for different values. Now, when we take a look at this, you can see if we look at our position function, our solution to the differential equation, and that thing I had you plot, we can identify terms. So in our little experiment here, y in the Google plot is taking the place of our position x of t, and x is taking the position of our time. So that's our independent variable, that's our dependent variable. This a is, at least for right now, has a value of 1. This delta has a value of 0. All right, so what we want to do is we want to play around with this a little bit and see how varying these quantities, A, omega, and delta, change that plot. All right, so here's what I want you to do. I'm going to have you pause this video now, and I want you to play with this. And I'm going to lay out for you here a couple things I want you to do. Go back to that equation you entered into the Google screen. And I want you to change the A value. Currently, the A value is at 1. Change it to a half. Change it to 2. Change it to 10, and see what happens to the plot. Take a minute, take a few minutes, write down a sentence or two in your notes to explain what happens to that plot. What does it look like? Take screenshots if you like. That's probably not a bad idea. You can compare these things side by side. Write down a few sentences to explain what happens when you change A. I want you to repeat that process. Go back to the original equation that you entered into the Google search bar and change the omega value. Change it to a half. It started out as 2, change it to a half. Change it to 1, change it to 4, change it to 8. Play around with it. And again, write a sentence or two to explain what happens. The last thing I want you to do is, again, reset to the original equation, and now we're going to play around with delta. Delta started out as 0. Let's look at a couple different delta values. Negative 1.5, negative 1, negative 0.5, plus 0.5, plus 1, plus 1.5. Take a look at those. Again, write up, make a couple of screenshots perhaps, and so that you can compare these more easily. Write a sentence or two of explanation. Please do that. And then pause this video, do that, and come back after you have done that. I'm going to have you write down your sentences here on Socrates as a little homework assignment, so don't skimp on it. Okay, let's move on and let's talk a little bit about what these are. So this quantity A is called the amplitude. It describes how far the object moves from the equilibrium position. So again, remember that this plot is describing the motion of this object back and forth on the end of this spring. So A describes how far this object moves from that equilibrium position. It's not the whole length of the motion, it is the distance from the equilibrium position to the furthest extent. Now, if we go back and look at that graph, A is going to be 1/2 of the total height of the plot. We call it for the trough to crest height. So if we come back to our Google plot here we see an A value of 1. The height of that plot from the equilibrium is 1. The depth is 1. So the total trough to crest height is 2. A is half of that at 1. A should be in whatever units the left-hand side of the equation is in. Since we're measuring position, where this thing is with respect to the equilibrium, A has to be a position. It has to be a distance in meters or something like meters, centimeters, inches, furlongs, whatever. Okay. Omega is the angular frequency. Now, you've seen an omega before in this class last term, the angular velocity omega. This is actually related to that, but it's not quite the same. So omega describes how rapidly the cycle repeats. You should have seen that larger values of omega make more of the squiggles closer together. Smaller values of omega spread those squiggles out. So this tells us how quickly that cycle repeats itself. Delta is a term called the phase angle. And really all it does is it tells us when to start. It tells us what's happening, what the motion of this object is at time t equals 0. So you can imagine, for example, if we come back to our plot here, this plot says that at time t equals 0, our position is maximum. So this is what happens if we've pulled this mass all the way out, and at time t equals 0, we let go. But if we'd started this thing off in a different way, say at the beginning, when we started time, instead of pulling the object out and letting it go, we had it sitting at equilibrium and we hit it, so that it starts off with a large velocity but with a 0 position. The resulting motion is going to be exactly the same. It's just starting at a different part on the graph. So if we smacked this thing, and so it started moving in the positive direction at time t equals 0, perhaps we would have started here. This could have been time t equals 0. It starts at 0 position and starts moving away from equilibrium. Or this could be position 0 right here, and it starts moving away from equilibrium. So delta allows us to set what the initial conditions are, and that's really all delta does. Now, go back and look at those screenshots that you took from that little experimentation, and what you should notice is that whenever we adjust any one of these parameters, A and omega and delta, none of those have any effect on the others. So if you change A, if you change the amplitude, that doesn't change the frequency. If you change the phase angle, that doesn't change the amplitude. None of those affect each other. They are completely independent parameters. All right. So we want to talk a little bit about how we talk about that angular frequency. And again, if you've talked about this if you've talked about radians in the first term, bear with me as I go through it again here. Okay, so what you can notice, if you come back and look at our function, I'm going to drive back over here. There we go. If we look at our position function, x of t is equal to a cosine omega t plus delta. The argument of the cosine function has to be an angle. And so each one of those things that we are adding also have to be angles. Anything we add together has to have the same units and has to have the same units as a sum. So each of those things is an angle. So omega t is an angle. And this is why we call it an angular frequency. We're multiplying this thing by time, so omega has to have units of inverse time, or angle per inverse time. The sine and cosine functions repeat every 360 degrees. If you go back and take a look at that plot, any of the plots that you've looked at, they'll repeat every 360 degrees. And it becomes convenient to introduce the unit of radians for a number of reasons. It'll become more clear as we go on. 1 radian is just a unit of a way to describe an angular unit, or it is an angular unit. So 2 pi radians is a full circle. 2 pi radians is equal to 360 degrees, so that 1 radian is about 57.3 degrees. Radians are going to end up being the natural unit and by natural I mean a very appropriate unit that derives from our mathematics. Okay, so let's talk a little bit about time. And what we want to do is take a look at our equation of our position equation and see how the period, the time of the oscillation, falls out of this equation. So one way we can think about the period of the oscillation is the amount of time it takes, the smallest amount of time it takes for the oscillation to get back to where it started. We can certainly come up with longer amounts of time for it to get back to where it started, but the period should be the shortest amount of time it takes to get back to where it started. So we can represent that mathematically in that first line. The position at some time plus that period time is equal to the position at the earlier time. So all we're going to do is we're going to take our position equation, our position is a function of time, and substitute it in here so that we have a of cosine omega t plus t, t plus little t plus big T, and over here we're just evaluating this position function at the earlier time. So we're going to do a little bit of algebra, and I'm going to adjust this just a little bit so that I can see that a cosine omega t plus delta plus omega big T is equal to a cosine omega t plus delta. So these arguments are exactly the same, except we have this extra omega t in here. Now, the cosine function repeats itself every 360 degrees, every 2 pi radians. That means this thing has to have a value of 2 pi in order for this cosine and this cosine to have the same value. So omega t must be equal to 2 pi, so t must be equal to 2 pi over omega. Now remember we said that the bigger omega is, the faster the repeat is. The more squiggles there are in the same amount of time, the more oscillations there are. That must mean that the period t is smaller. So big omega in the denominator, smaller period. We define a different frequency, we call the cyclic frequency, to distinguish it from the angular frequency. We define a cyclic frequency f. Now we often abbreviate that and we just refer to it as a frequency, but this thing is the number of full oscillations or full cycles that take place each unit time, so each second. We talk about a frequency, so for example, while the electricity that comes from that is in the United States in our wall outlets is 60 hertz, oscillates at 60 cycles per second. There's 60 full oscillations of that electric current in that is supplied by that wall outlet. That frequency is equal to the inverse of the period. So we can write it as shown there in equation 15. Units of cyclic frequency are inverse seconds, which we generally give the unit hertz to after Heinrich Hertz. We'll talk more about him later on in the term. And we write it with the symbol capital H lowercase z. And then, of course, we can manipulate that equation 15 to tell us how the angular frequency omega, the cyclic frequency f are related. Because one cycle contains 360 degrees of oscillation, or 2 pi radians of oscillation, it should come as little surprise that the angular frequency is 2 pi times the cyclic frequency. All right. Ooh, apparently I have an equation problem here. All right, never mind that. Let's come back and look at this. Clearly, down here in equation 16, 2 pi has no units. So it looks as if omega and f have the same units. And in some sense they do. Their units are essentially both per second, but they're really different. There's a phantom unit in here. The units of omega really are radians per second. And this 2 pi actually has a sort of phantom unit too. It's 2 pi radians per cycle, so that things cancel out. The important gist of this is, when we talk about f, we are really looking at cycles per second. even if we just write it as a per second and we call it a hertz, it's really, there's this sort of invisible cycles in there. Omega has this invisible radians in there, so it's radians per second. Now, both of those we can write as per second. But while this per second is a hertz, a cycle per second, this one is not. Be very careful with this. Now, I've got a general rule that you will find out, which is never write numbers until you absolutely have to. And whenever you do write numbers, make sure you write the units. This is critically important to help you not make mistakes. So here's your first place where you can make a mistake. Don't write in units. When you're writing in numbers, rather, make sure you get those units correct. We never express angular frequency in hertz. All right, let's go back to our angular frequency equation. We had found when we plugged our position and acceleration functions into Newton's second law, this relationship that said omega squared is equal to k over m, or rewritten here, omega is equal to the square root of k over m. Take a moment and think about this. What happens to the physical system when we change k, when we change m? Take a moment and think about this. If we use a heavier mass, what happens to omega? How does the value of omega change? And how does the resulting value of the period change? If omega gets big, what happens to the period? If omega gets small, what happens to the period? We need to remember as we sit here working on physics that the whole purpose of physics is not just to solve some equations. Physics is all about seeing a physical situation, translating that into a mathematical description that we can manipulating it, and then translating it back so we can understand something about the world. So let's take a look. If we make the spring stiffer, k gets big. And even under the square root, that's going to mean that omega is going to get bigger. So the bigger omega is, the smaller the period is. So if the spring is stiffer, that means that the oscillations are going to be shorter. Whatever that mass is going to vibrate faster in place. The bigger the mass is, the smaller omega is going to be, which means the larger the period is going to be, the longer it's going to take for this thing to move back and forth. So we can start to see how these different parameters, how the physical components of the system will affect the behavior of the system. Now let's go back and put all this together and think about how the simple harmonic motion works. I've got equations 5, 6, and 7 from earlier in the presentation here listed at the top of the screen. On the right-hand side, I'm going to show plots of these. And if you take a look at these plots, you can see that upper plot, the displacement, the position, is a cosine function. Here with a cosine function with delta equal to 0. Velocity looks like a negative sign function. It starts at 0 and drops. The acceleration function does look like a negative cosine function. So these plots do match up. They each have the same angular frequency omega. So you can see that the period, the time, say from crest to crest, the time from crest to crest, the time from crest to crest, and each one of these is the same. So what I want to think about here, again, is how do all these pieces fit together? What does each graph tell us about the motion? It's easy. We can look at this and we can say, well, sure, the displacement is high, is maximum at one point, then it goes back to 0, then it's maximum at the other direction. We're oscillating back and forth in time. Perhaps the mass is all the way out at the rightmost extension. It goes through the equilibrium, and then it's at the leftmost extension, and then it goes back through the equilibrium, and it's at the rightmost extension. I won't keep going on. And we can kind of do the same thing with velocity. Well, we're going fast, and then we're not moving, and then we're going fast in the other direction, and then we're not moving. And we're changing direction. Here we have a positive velocity, and there we have a negative velocity. We keep going back and forth. And we can do the same thing with acceleration, but really that's not the interesting part. The interesting part is what happens at any given slice of time. So here we go. Let's start at time t equals 0. What's actually happening at time t equals 0 in this plot? The position is at its greatest. So the mass is all the way out. At that instant, the velocity is 0. And the acceleration is large and negative. Wait, does that make sense? Maximum position, 0 velocity, and the greatest possible acceleration. Go back and look at our sum of forces equation. The greatest acceleration is going to occur whenever the position is greatest, but it's going to be in the opposite direction. So if the object is all the way out in the positive direction, the acceleration should be negative and maximum. So we have 0 velocity, we have negative acceleration. What happens? Go back to our kinematics. Now we can't use kinematics equations to describe this because the acceleration is changing, but there is a little bit of the concepts here that we can certainly discuss. When the velocity is 0, the acceleration is negative, this object should speed up in a negative direction. Well, look, there it is. It's speeding up. Its speed is increasing, but in a negative direction. As it does so, it moves back away from the largest positive displacement back towards equilibrium. At equilibrium, our position is 0, and this thing has sped up as fast as it possibly can go. We're at maximum velocity. But because we're at equilibrium, the force has dropped to 0. Now, we hit equilibrium. We don't stay there. Even though the net force here is 0, the acceleration is 0, we have a very large negative acceleration. We move through equilibrium. And as soon as we start moving through equilibrium, we start stretching the spring in the other direction, compressing it perhaps. And as we compress the spring, the force is directed back in the positive direction again. So the acceleration becomes positive, and that starts slowing down the velocity. So we can look at this plot and fully interpret this as describing the physical motion of that mass on the spring. All right, so let's try a little bit of a problem here and actually put these equations to work for us. I've got a case here. We've got a butcher puts a cut of beef on spring scales. If you're not happy about that, we've got a grocer who throws a head of lettuce on a scale. The scales oscillate about an equilibrium position with a period of a half of a second. The amplitude of the vibration is 2 centimeters. I want you to find the frequency, the maximum velocity, and maximum accelerations of this object. I want you to find the equation of I have no idea what I was trying to say there. The equation is a function of time. I must have meant the position. The position equation must be the drop term there. That x of t is equal to a cosine omega t, and find the acceleration and velocity each at 1.85 seconds. Go ahead and try that out. Pause the video now and resume it if you get stuck, or if you get done and you want to try checking your answers. All right, I assume you've taken a stab at this. Let's take a look at it ourselves. So the first thing I want you to do, always, is draw a picture. So here's my fantastic artwork here. See, there's a scale. There's a base of the scale, there's a spring, there's a platform of the scale, and here is that head of lettuce, conveniently drawn as a square, on the scale. And there's our equilibrium position, y equals 0. And this thing is going to oscillate about that equilibrium position with an amplitude of 2 centimeters. So it's going to go 2 centimeters up, 2 centimeters down. That's a huge oscillation for a scale, but we're going to go ahead and leave it that way because we want to be able to see it. So big oscillation here. Now we'll note, well, the a over 2 we've left for later. Okay. Always start with a picture. Here I've also labeled the period of the oscillation. So the first thing we can do is, if we know the period, we can quickly determine the cyclic frequency and angular frequency. So go and take a look. If you got stuck, take a look at equations 14 and 16. There's a little hint. Try that now and resume when you've solved those. Okay, I assume you've solved for the frequency and angular, the cyclic frequency and the angular frequency. Let's take a look. You should have looked at equation 14, where we have the period is equal to 2 pi over omega. We can solve that thing for omega and come up with an expression that looks like 2 pi over 0.5 seconds. Our period was, I seem to have miswritten that on my picture, right? The period is 0.5 seconds, amplitude of the vibration is 2 centimeters. So that, of course, doesn't make any sense. You probably caught that before, but I didn't notice. 2 pi over our period gives me about 12.6 radians per second. If we use equation 16, we can find that the frequency looks like omega over 2 pi. 12.6 radians per second over 2 pi gives me about 2.00 per second, or 2.00 hertz. Now, you could have looked at this and realized pretty quickly that because cyclic frequency is 1 over the period, you could get to your 2 hertz answer there that way as well. All right, let's go and take a look at the SHM position function. Again, if you need that hint, the SHM, the simple harmonic motion position function, is given in equation 5. Go take a look at that and see if you can figure out what you need to solve it. And let's see how you did. Okay. We know that the amplitude is 2 centimeters. We've already figured out omega. So if we wanted to plug those things in here, here we go. We've got almost everything except for delta. How do we find delta? Well, here's where the initial conditions come in handy. We're told that at time t equals 0, the position is half of the amplitude. So let's take this and write it out for time t equals 0. X at t equals 0, we're told, is a over 2. And that must be equal to the amplitude, which is 2 centimeters, but we don't need that information now, so we're not going to use it, times the cosine of omega times the time at 0 seconds, plus delta. So I can divide a out of both sides, gives me 1/2 is equal to cosine of delta, because of course omega times 0 is 0. Delta is equal to the arc cosine of 1/2, which is equal to 60 degrees, or pi over 3 radians. So then our position equation is very simple. X of t is equal to 2.00 centimeters times the cosine of 12.6 seconds times t plus pi over 3 radians. Ta-da! And I did not get to the remaining pieces here. So let's just sort of take care of this on the fly. Here's what I want to do. Let's go and take a look at these equations right here for a moment, and we'll talk a little bit about maximum velocity and maximum acceleration. Look at equation 5. The cosine function and the sine function, all of our sinusoidal functions, vary between values of 1 and -1, which means that x is going to vary between values of a times 1 and a times -1. So it varies between -a and +a. In the same way, look at our velocity function. What's it going to vary between? Sine varies between 1 and -1, and we're going to multiply it by this thing. So our velocity function is going to vary between values of -a omega to a omega. That's shown right here in this plot. There's a omega. There's minus a omega. So our maximum velocity is this coefficient, a omega. In the same way, the acceleration function is going to vary between a omega squared and -a omega squared. This is our maximum acceleration. So while I apparently did not finish that solution here for the presentation, we can now go and calculate the maximum velocity. Oops, where are we? We can calculate the maximum velocity and the maximum accelerations. This is a omega. This is a omega squared. As maxima, we don't need to include the negative sign. We're just going to leave it as a positive quantity. The last components we need to do then, having found the maximum velocity, the maximum acceleration, we can write out all three of our equations. And so steps 3 and 4 are very trivial. Now we can go and we can take and solve. Since we have our position function there, we can throw in any particular time we want, 1.85 seconds or whatever, and solve for position, and do the same thing with our velocity and acceleration plots. Try those out on your own. Make sure you understand what's going on there. Now, our last topic for this particular presentation is to talk a little bit about circular motion. There's a relationship between motion in a circle and our simple harmonic motion. What I want you to imagine is going to the park, to the merry-go-round. We have a child sit on the merry-go-round. We'll spin the merry-go-round around, let it go at a nice constant speed, and sit down and watch that child from the side. So here we have a picture which could be a merry-go-round seen from the top. We've got a child sitting here at point P, and you're going to sit somewhere over here looking at it this way. So as you see the child go around and around, you don't see this position change towards you, away from you very effectively. You do see the child move back and forth side to side. So essentially, when you measure the child's position from the side, you're measuring this X position right here. Now, the radius of this circle, shown here as a big X, that's a constant. The child is turning this big X circle. But the small x is this, and you can quickly see that that's going to be a component of this vector. So this little x is going to be equal to the radius multiplied by the cosine of this angle. So it's going to look like a cosine, if we think of that x, well, wait a minute. When x is all the way out here, this represents the furthest distance. Sorry, when the child is sitting over here, this represents the furthest distance the child is away from that center point. So we could call that plus a. And we come around here, they're going to be the furthest distance away from the center point on the other side, negative a. So essentially, we could describe the child's position, this little x, as a cosine theta, where a is just equal to the radius x. And because that theta can be described as an angular velocity or angular frequency multiplied by time, we end up with this x. It looks exactly like cosine omega t. Now we left off the delta. We could have thrown a delta in here to indicate where the child is at time t equals 0. Take a look at this YouTube video. And this will give you a little animated example of this. It might help you understand a little bit better. Let's do one more example here before we stop. Let's consider a car with 28.5-inch diameter wheels. It's traveling down the road at a constant speed of 50 miles per hour. There's a point on the rim of the wheel, the steel rim of the wheel, and it's going to be describing this simple harmonic motion in an up-down sense. It's up and down. It's going to be moving up and down vertically in a motion that looks exactly like simple harmonic motion, because the equation is going to look like essentially just like this. We want to write out the position function for that vertical motion. All right, our rim has a diameter of 16 inches, and I'll tell you right now that I realized as I was drawing up a picture for this, which I did after the math, I did not check to see if I took diameters or radii. So the first thing let's do is convert all of our quantities here to MKS units and make sure we have radii and not diameters. So let you do that. Convert your inches to meters, convert miles per hour to meters per second. Draw a picture. There's a picture, and here in my picture I did the right thing. So, unfortunately, my battery is about to run out, so we may not get to finish this problem. I may not get to finish talking you through this problem. We'll see how far we get. The tangential velocity must be equal to r omega. You should have seen this when you did angular motion, rotational motion last term. So that 55 miles per hour in MKS units is equal to r omega. So we can solve for omega by taking that tangential velocity divided by radius. The amplitude of the motion then is the radius of the wheel, and therefore we have A, we have omega. Let's set delta equal to 0 for simplicity, and we can write out our position function. And rather than losing our video, I'm going to stop it now, and you can give you guys a chance to start on some homework. Thank you.